This is part 2 of the midterm review. This is for chapter 3 for this textbook, Calculus for the Life Sciences. It's by no means comprehensive, so it should be in addition to your own studying. I'm mostly going to cover the concepts here. For more practical examples, ask chapter questions in the DGD. Okay, so this is the review of chapter 3, Limits, Continuity, and Derivatives. Chapter 3.1 is just supposed to give you an idea of what the chapter is trying to get across. And it's using the concept of a limit. We're going to examine some sort of continuous function, and we'll later define a derivative. But what the derivative is, if you take any 2 points on the graph and you join them with a line, and you move those points closer to each other, you draw another line. Eventually, once you approach a point, you'll get a line. And this line will be the instantaneous rate of change at that point. And the slope of that line will be the derivative evaluated at that point. A more in-depth mathematics class will go over this sort of thing, but we want to really quickly get to it so that we can use it in useful ways. So the first thing to talk about is what a limit is. And there's 2 parts of a limit. The function and the domain. As x gets closer to r on the domain, the output of the function is closer and closer to L. I would hope by now that you are familiar with the direct substitution rule. If a is in the domain of f, then the limit as x approaches a of f of x is equal to f evaluated a. But this is only true for very special f. And the book says f has to be algebraic, exponential, logarithmic, trigonometric, or inverse trigonometric. So basically, nice functions. If a function is nice, then the direct substitution rule applies. But there's plenty of cases where you have some graph and there's a point that's been moved just at that point. And if you look, the limit will actually be here where the point is missing, but when you evaluate it, it's here. So this equality doesn't hold. It's only when the function is nice and simple and usually not point-wise defined. On page 175 of your textbook, Theorem 3.1, the properties of limits, is very, very useful. But it's important to note when it applies. This Theorem 3.1 starts with, suppose f of x and g of x are functions such that the limits as x approaches a of f of x and g of x both exist. So what that means is that limit as x approaches a of f of x has to equal some L, some number that's actually a real number. So in order to exist, it has to actually equal a real number. It cannot be infinity. And the limit of as x approaches a of g of x also has to equal, let's say this is L1, this is L2. And it's a good idea to go over them. The limit of the sums is the sum of the limits. The limit of the difference is the difference of the limits. One important one, limit as x approaches a, when c is some constant, c times f of x, is just c times the limit as x approaches a of f of x. That's the constant multiple rule for limits. And the most useful of all would be the product rule. The limit as x approaches a of f of x times g of x, when both f of x and g of x exist and equal real numbers, is just the limit of each one multiplied. So these are very useful and can make questions easier. If you know that two limits are defined, you can split a product up and just tackle each part. Just to restate a very important idea, say that we have three graphs that are similar except for one minor difference, is that in this case it's defined everywhere. In this case it's not defined for this point. In this case it's not defined there, but we've created another point there. Right here in each graph, the limit will equal the same thing, even though it's not defined here, and even though it's been moved here. The limit it's of f of x as x approaches a, and the big part of that is that it's approaching a. It's not actually at a. It's what does f of x tend to as we get closer. And as we get closer in each graph, we're getting closer to the same thing. You're more than likely going to be asked a question that along the lines of, does this limit exist? And a limit is said to exist if the right-hand limit and the left-hand limit both equal the same real number. If the limit does not exist, there's two cases, and you should always give as much information as you can. And so it will be important to note whether it does not exist because it diverges to infinity, or because there's a lack of uniqueness. And the case where it diverges to infinity is when the limit of the function gets way too big, either too big to positive infinity or too big to negative infinity. And the lack of uniqueness is when the right-hand limit does not equal the left-hand limit. I urge you to read page 194, definition 3.7. It goes over the case where two limits diverge to infinity, and we're talking about the quotient of them. Because sometimes, if we have f of x over g of x, and we're taking the limit as x goes to infinity, sometimes this will diverge to infinity as well. Sometimes it will actually, the limit will be 0, and sometimes it will just be a real number. And it depends on whether the two functions, which one diverges faster. There's a table on the next page, page 195, table 3.3.7, which goes over all the cases and gives you an idea of what is faster. For polynomials, it's what has the bigger exponent. If f of x has a bigger exponent than g of x, so say it's x4 plus x3 over x2, the limit as x goes to infinity, the top is bigger, so this one will go to infinity. But say g of x is faster. If we have x3 plus x2 over x to the 5. X to the 5 goes way faster because it has a bigger exponent, so this will go to 0. And if they're the same, if we have x4 plus x3 over 2x4 plus x, this one will go to the constants with the exponent of the top one and the constants of the exponent of the bottom one, so it will go to 1/2. We did some examples of this in one of the DGDs. Refer to your DGD notes. I simply don't have enough time to go over all the different ones, but one that I will go over, let's do the limit as x goes to infinity of 3x squared plus x plus sine x over 4x squared. Think about what that trigonometric function is. And sine x oscillates between -1 and 1. So it's a bounded function. It can't get big. So we don't even have to worry about sine x in this case. All we're worried about is the biggest exponent in this case and the constant with each one. So this limit goes to 3 over 4. You can show this a little bit more elegantly by timesing both sides of the fraction by 1 over x squared. And I would suggest doing that if the question calls for some rigor. All I'm going to say about continuity is the definition and a few remarks. If you need help with continuity, bring it up in the DGD before the midterm. So the definition is a function f is continuous at a if the limit as x approaches a of f of x equals f of a. So basically, a continuous function is one that we can use the direct substitution rule for. There's some remarks about this definition. Well, first thing is, a continuous function is one where any a, if we choose any a and to take the limit as x approaches a, this will hold. So so a function is continuous at a point if this holds, and if it's continuous at every point, the function is continuous. It's discontinuous otherwise. Few remarks. This limit is a real number. The function has to be defined at a, and the limit and the function at that point have to be equal. Okay, so the last thing for this chapter is the definition of the derivative. Derivative at x is the limit as h goes to 0 of f of x plus h minus f of x all over h. Let's just do the derivative of some simple example. How about f of x is equal to 2x plus 3. Alright, so the limit as h goes to 0 of f of x plus h is 2x plus h plus 3. We just plug x plus h into our function, and we subtract 2x plus 3. That's just our function evaluated just x. We notice that the 3's cancel. We're dividing by h here. So this is equal to the limit as h goes to 0 of, we also notice that this x cancels with this 2x of 2h over h. The h's cancel, and the limit of some constant is just the constant. So the derivative at x, this is f prime at x, and the derivative at x is 2. So this derivative is defined everywhere on the domain, which is all real numbers because the natural domain of f is all real numbers, and the derivative everywhere is 2.